Last week, we talked about what a derivative is, how to interpret a derivative in real-world contexts, and also how to understand a function in terms of its own derivative. We didn't really talk about how to compute derivatives, though, so some of that information wasn't particularly useful to us. The only method that we talked about last week for computing a derivative was the definition, using this pretty gnarly limit to try and compute a derivative. This week, we're going to talk about derivative rules and some standard derivative computations that will allow us to compute a derivative of pretty much any function we can think of without having to write down the limit definition. I'm going to use the word rule to mean a way of combining information about the derivatives of some functions in order to compute the derivative of another function. For example, if I have two functions f and g, I could add them together and then take the derivative. It turns out that that's equal to the sum of the derivatives. This is called the sum rule. There's a lot of other derivative rules that each have a name. I won't track through them, but I am going to point out a few things about them. Each one of these rules I've stated in two different ways, with the prime notation and with the d by dx notation. The prime notation is due to Isaac Newton, who, as you can see, was a little bit of a looker, but it's a pretty weird, scary dude. Leibniz, maybe not so much to look at, but he was definitely not completely weird like Newton was. Each of these rules has a name. You can basically guess what the rule is about by its name. So the sum rule is about the derivative of a sum, the product rule is about the derivative of a product, the quotient rule is about the derivative of a quotient, and the chain rule is about the derivative of the chain rule is about the derivative of a composition. We'll come back to the chain rule later. A couple of tips for you here. I remember the product rule and the quotient rule in the following way. I always write f and g in the same order they appeared over here. So f appeared first, so you see in each of these two terms, f appears first. In the first case, it's f prime. In the second case, it's f times g prime. The other thing to remember about the quotient rule is that whatever goes downstairs started downstairs, and as long as you differentiate f first, you'll never forget the order. In addition to rules, I'm going to have what I call formulas. These are derivatives of particular functions, or sometimes of a particular class of functions, that basically you just need to memorize. These are the only ones we're really going to need. We will see how to find the derivative of any function we can think of just using these basic building blocks. This is sometimes called the power rule. It's not really a rule, it's really a formula. And I want to say there's one important thing to remember, which is that when n equals 0, this rule doesn't apply. That'll come up a lot more later. So let's show off our tools. Let's see if we can use these rules to differentiate a function. And the hint here, the tip I'll give you, is that you really want to use the Leibniz notation. You may be used to primes, they may be friendlier, but the d by dx notation is really, really useful. And I think that's going to become apparent as we do these derivatives. So let's just charge in. This function is not a particularly simple function, but it's also not particularly complicated. So let's go ahead and see how we can use all the various rules of derivatives to compute the derivative of this. The first step is the decision to use Leibniz notation. Then we have to recognize this is a composite function. The outside function is the operation of taking the input and setting it as an exponent to the base e. And then the inside function is square root x squared plus 1. The chain rule tells us we need to know the derivative of the outside function. In this case, the derivative of e to the t is e to the t. The chain rule tells us write that derivative down, evaluate just like it was, and then differentiate whatever was inside. Now I do an algebraic step. It's not really a calculus step. I just realized that the square root is really the 1/2 power. Now again, I have a composition of functions. The outside function is the square root function, which I can think of as the 1/2 power function. And I use the power rule, which is just a formula, to compute the derivative of z to the 1/2 as 1/2 z to the minus 1/2. The inside function is x squared plus 1. So I apply the chain rule. My derivative now falls on a sum, so I use the sum rule. You can think of this as distributing the d by dx. Now the functions x squared and 1 are easy to differentiate. I apply those formulas, and I do a little bit of algebraic cleanup. There we go, that's our final answer. That's f prime. This example really sort of busted our chops. We had to use many of the rules of derivatives in a single problem, and that's okay. Let's do another example. Again, we recognize that this is a composition, so we need to know the derivative of the outside function, in this case, the sine function. Now the derivative falls on a product, so we need to use the product rule. Now we simply apply the formulas that we know. And as usual, we do some algebraic cleanup. Let's do one final example. Again, we need to apply the chain rule first. Now we apply the sum rule. And now we're ready to apply some formulas. And as usual, we clean up after ourselves algebraically. So that's it. That's how you differentiate. You apply the chain rule when you need to, when you see a derivative of a composition. You apply the product rule when you see a derivative of a product. And you apply the sum rule when you see the derivative of a sum. As long as you do the bookkeeping correctly, and that's what this Leibniz notation, the d by dz in this case, that's what that helps you do. As long as you keep applying that d by dz until, at the very end, there's no more d by dz's left, and then you're done, except if you want to algebraically clean up a little bit.